Hello everyone, and welcome. I'm excited to kick off this presentation on three-dimensional geometry. Today, we'll explore the fascinating world of 3D space, covering key concepts and applications. So, let's get started and delve into this intriguing subject together. Let's explore some fundamental concepts related to lines and planes in space. First, we'll look at the angle between a line and a plane, which helps us understand how these two geometrical elements relate to each other. Next, we'll examine how a plane passing through the intersection of two other planes can be determined, a key idea in constructing complex surfaces. We'll also touch on some notes that clarify important properties, and then move into the concept of skew lines, lines that do not intersect and are not parallel, highlighting their significance in space geometry. Following that, we'll review the equation of a line passing through a point, specifically in Cartesian form, which is essential for defining lines in coordinate systems. An example will help concretize this concept. Then, we'll discuss the distance from a point to a plane, a critical measure in many applications, and look at the intercept form of a plane's equation, which provides an intuitive way to understand its position. We'll also cover the normal form of a plane's equation, which involves the plane's perpendicular vector, making it easier to analyze orientations. Moving on, I'll present an example illustrating these ideas, and then we'll examine the vector form of a line passing through a point, offering a different perspective for describing lines. Next, again, the distance from a point to a plane will be revisited, emphasizing its importance. We then consider the direction ratios of a line segment, which help us understand the line's orientation. The equation of a plane passing through three noncollinear points provides a way to define a plane uniquely, which is essential in 3D geometry. Coplanarity of two lines, meaning whether they lie in the same plane, is another crucial concept, especially when analyzing complex systems. We'll look at the distance between parallel lines, a measure of how far apart they are, and then the angle between two lines, which tells us about their relative orientation. Furthermore, we'll see how to find the equation of a plane perpendicular to a given vector passing through a specific point, a handy tool for constructing planes with desired orientations. The equation of a line in space will be reviewed again, reinforcing its importance, followed by the shortest distance between skew lines, which is vital in spatial analysis. We'll revisit the direction cosine of a line passing through 2 points, providing a measure of its orientation in space. The equation of a line passing through 2 given points will be covered, offering a fundamental method for line definition. An example will help tie these ideas together. Finally, we'll revisit the direction cosine of a line, emphasizing its role in understanding spatial directions. All these concepts build a comprehensive understanding of lines and planes in three-dimensional space, which is central to our overall study of spatial geometry. Today, we're going to talk about direction ratios, which are also known as direction numbers. These are important because they help us understand the orientation of a line in space. Now, when we refer to the direction cosines of a line, we're talking about the cosines of the angles that the line makes with the coordinate axes. Essentially, these cosines give us a way to describe the line's direction in a very precise way. The key point here is that the direction cosines are fundamental because they help us define the line's orientation using angles. But there's also another way to look at this, which is through direction ratios. These are proportional to the direction cosines, meaning they give us a similar sense of direction, but are often easier to work with in calculations. So, when we talk about the direction cosines of a line, think of them as the cosines of the angles between the line and each of the axes. These are crucial in vector analysis and in understanding how a line is positioned in space. Connecting this to our overall theme, understanding these concepts allows us to analyze lines more effectively, whether for geometric problems or in applications like engineering and physics. Let's take a closer look at this example. Here, I want to highlight how the key concepts we've discussed come together in a real-world scenario. This example helps illustrate the practical application of the ideas and shows how they can be effectively implemented. Notice how each point connects back to our overall theme of understanding the process and improving outcomes. By examining this example, you can see the concepts in action and better grasp how to apply them in your own work. It's a valuable way to bridge theory and practice, making the information more relatable and easier to remember. A line is uniquely determined if it passes through a given point and has a given direction. This means that once we know a specific point on the line and the way it's oriented in space, there's only one line that fits those criteria. Additionally, a line also passes through two given points, which essentially defines it uniquely. If you know where 2 points are, the line that connects them is fixed. Now, moving on to the next part, we'll explore how to express the equation of a line in space, which is fundamental for understanding the geometry in 3 dimensions. This concept ties into the overall theme of accurately describing lines and their positions in space, which is crucial for a wide range of applications. Today, we're going to look at how to find the equation of a line that passes through a specific point and is parallel to a given vector. This is a fundamental concept because it helps us understand how lines relate to each other in space, especially when dealing with directions and positions. The key idea here is that if we know a point through which the line passes and the vector that indicates its direction, we can write the equation in what's called vector form. This form is very powerful because it encapsulates all the information about the line in a compact and elegant way. Remember, the vector form essentially combines the position vector of the point with the direction vector, giving us a complete picture of the line's path. This approach is especially useful because it makes it easy to visualize and manipulate lines in 3-dimensional space, or even in higher dimensions. As we connect this to the overall theme of the presentation, understanding how to derive and work with this form is crucial for solving more complex geometric problems and for applications in fields like physics, engineering, and computer graphics. So, mastering this concept sets a strong foundation for everything that follows. Today, we're looking at the Cartesian equation of a line, which is a fundamental concept in coordinate geometry. Specifically, we'll focus on the equation of a line passing through a given point, expressed in the Cartesian form. This form is particularly useful because it allows us to directly relate the coordinates of any point on the line to a specific point it passes through. When we say passing through a point, we're referring to a known coordinate, say x1, y1, and then describing all other points x, y that lie on the same line relative to that point. This approach helps us understand the line's position in the plane and its slope, which is key in many geometric and algebraic applications. As we progress in this presentation, keep in mind that these equations are essential tools for analyzing and solving real-world problems involving linear relationships. Today, we're going to explore the equation of a line passing through 2 given points. This is a fundamental concept in coordinate geometry because it allows us to find the equation of a line when we know 2 specific points on that line. The key idea here is that a line can be uniquely determined by 2 points, and once we have those points, we can derive the equation that describes the entire line. First, we need to find the slope of the line, which tells us how steep the line is. The slope is calculated by taking the difference in y values and dividing it by the difference in x values between the 2 points. Once we have the slope, we use it along with one of the points to write the equation of the line in point-slope form. This form makes it straightforward to express the line's equation based on the point and the slope we've calculated. From there, we can rearrange the equation into slope-intercept form if needed, which is y equals mx plus b, making it easier to interpret and graph. Understanding how to derive the equation from 2 points not only helps in graphing lines, but also deepens our grasp of the relationships between points, slope, and line equations in the broader context of coordinate geometry. Now let's move on to slide 10, which is about the angle between 2 lines. When we talk about the angle between lines, we're essentially looking at how these lines are oriented relative to each other in space. This angle is important because it tells us about the line's relationship, whether they intersect, are parallel, or are skewed. To find this angle, we typically use the direction vectors of the lines. Key concept here is the dot product, which helps us calculate the cosine of the angle between the vectors. Once we have that, taking the inverse cosine gives us the actual measure of the angle. Remember, this angle always falls between 0 and 180 degrees. Understanding this helps in many applications, from geometry problems to real-world scenarios like engineering and navigation, reinforcing the overall idea that angles reveal the spatial relationships between lines. Let's take a closer look at this example. Here, I want to highlight how the key points we've discussed come together in a practical scenario. It's one thing to talk about concepts in theory, but seeing how they apply in real situations really drives the message home. Notice how the example connects directly to our overall theme, showing the relevance and impact of these ideas in actual practice. By walking through this, I hope it clarifies how you can implement these strategies yourself and understand their significance in achieving your goals. So, if two lines in space intersect at a point, then the shortest distance between them is actually 0, because they meet at that point. Now, if two lines are parallel, the shortest distance between them isn't 0. Instead, it's the perpendicular distance, the shortest straight line segment connecting the two lines at right angles. But things get more interesting when we consider lines that are neither intersecting nor parallel. These lines are called skew lines. Skew lines are non-coplanar, meaning they don't lie in the same plane, and they don't intersect or run parallel. Understanding skew lines helps us see the complexity of spatial relationships beyond simple intersections and parallels, and it's a key concept as we explore three-dimensional geometry and how objects relate in space. Now, let's look at how we can determine the shortest distance between two skew lines, which are lines that do not intersect and are not parallel. This is a common problem in spatial geometry, and understanding it helps us solve many real-world issues involving three-dimensional space. The key idea here is that the shortest distance between these lines can be found using a specific set of equations. These equations are derived from the vector representations of the lines and involve calculating the perpendicular distance between them. Essentially, what we're doing is finding a line segment that is perpendicular to both lines, and its length gives us the shortest distance. This involves using the cross product of the direction vectors of the lines to find a vector perpendicular to both, and then projecting the vector connecting points on each line onto this perpendicular vector. By understanding these equations, we can accurately compute the minimum distance, which is crucial in applications like engineering, navigation, and computer graphics. So, mastering this concept ties directly into our overall goal of understanding spatial relationships and geometric calculations in 3 dimensions. Let's take a closer look at the distance between parallel lines. This is a fundamental concept in geometry because it helps us understand how two lines can be related spatially. When lines are parallel, they are always the same distance apart, no matter how far they extend. This constant separation is what we call the distance between the lines. Understanding this distance is crucial, especially when dealing with real-world applications like architecture, engineering, or even navigation. It ensures that structures are built correctly and that measurements are accurate. So the key idea here is that for parallel lines, this distance is fixed and does not change as you move along the lines. It's a unique property that sets parallel lines apart from other types of lines that might intersect or diverge. By grasping this concept, we're better equipped to analyze geometric figures and understand the spatial relationships between different shapes. And this idea of constant distance ties back to the overall theme of understanding how lines and planes interact in space. In Cartesian form, the equation of a plane can be expressed using the coordinates of any point on the plane, along with the normal vector. This form is particularly useful because it directly relates the position of points to the plane's orientation. Now, when we talk about the vector form of the equation, we're essentially describing the same plane, but in a way that highlights its normal vector and a specific point on the plane. This approach makes it easier to understand the geometric relationships involved. Moving forward, we'll see how these forms connect to the normal form of the plane equation, which emphasizes the perpendicularity of the normal vector to the plane itself. Understanding these different representations helps us grasp the underlying structure of planes in three-dimensional space and prepares us for more advanced applications. Let's take a closer look at how we can express the equations of a plane using both Cartesian and vector forms. These two forms are fundamental because they give us different perspectives on the same geometric object. Now, when we talk about a plane that's perpendicular to a given vector, we're essentially specifying the orientation of the plane in space. The key idea here is that the normal vector to the plane is perpendicular to every line lying on that plane. And importantly, if we know a point through which the plane passes, we can use that point along with the normal vector to find the specific equation of the plane. This approach is particularly useful because it allows us to easily determine the plane's equation given just a point and a normal vector, which are often easier to identify in problems. So, in summary, understanding how to derive the equation of a plane from a normal vector and a point is a powerful tool in our mathematical toolkit, connecting the geometric with the algebraic and helping us visualize and solve problems more effectively. Now, moving on to slide 16, let's talk about how vectors and Cartesian equations can be expressed in different forms. As you can see, both the vector form and the Cartesian form are powerful ways to represent geometric entities, and understanding how to switch between these forms is key for solving many problems. Next, we'll focus on the equation of a plane passing through three noncollinear points. This is an important concept because, as you might recall, three noncollinear points uniquely determine a plane. The core idea here is that once you have three such points, you can find the equation of the plane that contains them. This involves calculating a normal vector to the plane, which is perpendicular to it, and then using the coordinates of the points to formulate the equation. Remember, the normal vector can be found by taking the cross product of two vectors lying on the plane. Once you have that normal vector, the equation of the plane can be written in a form like ax plus by plus cz equals d, where a, b, and c are the components of the normal vector. This method ties back to the overall theme of understanding different representations and equations in 3D space, allowing us to analyze and solve spatial problems more effectively. Now let's take a closer look at the intercept form of the equation of a plane. This form is quite intuitive because it directly shows where the plane intersects the axes. Essentially, the equation is written as divided by a plus y divided by b plus z divided by c equals 1. Here, each of these denominators, a, b, and c, represents the points where the plane hits the x, y, and z axes, respectively. These are called the intercepts. So, if we know the intercepts, we can write the equation of the plane pretty easily using this form. It's a very useful way to visualize the plane's position in space. It makes understanding the relationship between the plane and the axes much clearer. Throughout this presentation, we've been exploring different ways to describe planes, and the intercept form stands out because of its straightforward geometric interpretation. It helps us see exactly where the plane crosses the axes, which is foundational for understanding how planes interact with other geometric objects. Now, let's move on to slide 18, which discusses how vector form and Cartesian form can be expressed for lines and planes. Understanding these forms is essential because they provide different perspectives and convenience depending on the problem at hand. The vector form is great for visualizing directions and positions, while the Cartesian form translates these into algebraic equations that are easier to manipulate analytically. Both forms are fundamental in analytical geometry, and knowing how to convert between them allows us to approach problems more flexibly. Next, we'll explore the concept of a plane passing through the intersection of two planes. This is a very interesting topic because it reveals how multiple planes can be related through their intersection. When a plane passes through the intersection line of two other planes, it can be described using a linear combination of their equations. This idea is powerful because it simplifies the process of finding all planes that contain a common line. The key point here is that the general equation of such a plane can be expressed as the sum of the two plane equations, each multiplied by some scalar. This scalar acts as a parameter, giving us a family of planes passing through the same intersection line. It's a concept that ties together the geometric intuition with algebraic representation, reinforcing the overall theme of how geometry and algebra work hand in hand in three-dimensional space. Now, let's look at how vector form and Cartesian form can be expressed. These are powerful tools for representing lines, planes, and other geometric entities in a clear and precise way. Understanding these forms helps us manipulate and analyze geometric problems more effectively. Moving on to slide 23, which focuses on the distance of a point from a plane. This is a fundamental concept in vector geometry because it allows us to quantify how close or far a point is from a given plane. When we talk about the distance from a point to a plane, we're essentially measuring the shortest path, which is perpendicular to the plane. This shortest distance is crucial in many applications, from engineering to computer graphics. To find this distance, we use the plane's normal vector, which is perpendicular to the plane, and the coordinates of the point. By projecting the vector from the point to the plane onto the normal vector, we get the perpendicular distance. The key takeaway here is that this method gives us an exact measure of how far a point is from the plane, regardless of where the point is located relative to the plane. Understanding this concept not only deepens our grasp of vector relationships, but also connects to the overall theme of spatial analysis in 3 dimensions. It's a fundamental building block for more complex geometric and analytical problems.